recording the session now. Okay, so we will talk today about regression. So last time we ended with correlation, which essentially is the analysis of an association between two scaled variables, where the y-axis is on the dependent where the y-axis reflects the dependent variable and the x-axis reflects the independent variable. It's basically the logical continuation of correlation is regression. So correlation established an association using the correlation coefficient to quantify the strength of this association. And Emma, which is larger, minus 0.74 or 0.25 positive?
Minus 0.7.
Very good, thank you. Okay, so we have now the correlation that essentially gives you the direction and kind of gives you a way to quantify the strength of this association. Regression utilizes now the correlation to predict your dependent variable. And this is essentially an extremely powerful tool to have because you can predict virtually everything with the right equation. So this is consequently the logic continuation. So basically you can predict an individual score based of a dependent variable using the independent variable by basically relating the standardized scores, individual scores of the independent variable to the standardized scores of the dependent variable by creating the so-called standardized regression equation. So the relationship that is stated down here gives you essentially as the outcome the set y hat. And for all of you that continue in statistics, y hat will always indicate a predicted variable. So this is a prediction and regression analysis, all in regression analysis. The deeper you get into regression and statistics, you will try to predict more and more and more. You're doing this in the simplest form with a linear equation, with a simple linear regression by relating the standardized set score of x, of the independent variable, by utilizing the correlation coefficient that gives you an idea about the direction this association takes on, and to essentially quantify this predicted y hat. And we will do this today, and it's considerably simple and intuitive, but the calculations are a little bit more complex. So as an example here, you're building this regression by utilizing the variability and the means to standardize your predictor variables, your x. So you have -2, -1, 0, 1, and 2. And you basically, by that, you get, by utilizing the correlation coefficient, you get a predicted set score for your outcome variable. So this is what we will be doing. And so you essentially, you have the raw scores of your x for each individual that you have tested in your data set, and you're using these outcome x and the outcome y that you have observed to build a regression equation and use this regression equation for an estimate of a dependent variable for other individual hypothetically. And we will talk about this example. And this is not only important for population health statistics, this is also important on the stock market, for example. It's like on Wall Street, they mean to predict stocks, how they will evolve. And they use regression-based methods, quite more sophisticated as you can imagine, but they're doing essentially exactly that. So they take information from what they have observed and they try to extrapolate and predict it in the future. So how is this essentially done? So we will do today, we're going to deal with an example where we have a data set of 10 individuals. 10 individuals that have experienced a varying number of stressful life events. And we will have corresponding scores from the so-called back depression inventory. You have on the module, you actually have the original publication of Beck, which those of you that are going into psychology, this is the most commonly used depression survey, so to say. It's a questionnaire that basically has, I forget how many questions, but I think it's like 50 to 60 questions that will basically allow an assessment and a quantitative assessment of how depressed is this individual. And which you can imagine, as prevalent as depression is in our society, how important that essentially is to understand that when being in psychology. So we will analyze it. Essentially, what you see here is a characterization of these entries. We're building a mean, we're building a standard deviation, and we will be moving on then to determine this regression equation. So again, we want, in a perfect world, we want to predict our y hat with absolute certainty and accuracy. And this y hat is a prediction. In a practical example, as it's being used in predictive analytics, you develop regression model and predictive models where you're using these entries of 10 individuals and you quantify a number of stressful life events, back depression score, you develop an equation where this equation allows for you sit in your practice, you have a patient comes in and he says like, I'm depressed. And you ask the individual, so how many stressful life events did you have? And you can utilize this information to quantify how depressed is this individual and how do you treat the individual best. And this is simplistic and not true, but essentially this is the extrapolation of that thought. This is the continuation of the thought. So you mean to utilize data that you have at hand to predict something that comes to you in the future. So essentially this equation, just like all linear equation, contains of an outcome, a y. It contains an intercept, and the intercept is where your equation crosses the y-axis and x equals 0. What does this mean? So essentially you have here as the second term, you have here a b, which is your slope, multiplied by an x. So what I just said, y hat equals a, it equals the intercept is where x equals 0, because if you have x equals 0 and you multiply it with a slope, this becomes 0, so you add 0 to your a, so y hat equals a when x equals 0. This is arithmetically defined, but so a is the intercept, b is the slope. What does the slope mean? The slope is basically an increase of your dependent variable with an increase of 1 on the independent variable. Meaning when you have a stressful life events on the x-axis, an increase of 1 stressful life event will essentially increase the slope by a known and predicted extent. So if we zoom in here, the data set, we essentially have here, oops. I deleted one, just a second. I didn't manage that. I deleted one, okay. But did I manage that? Okay, so we have here this data from Nolan and Heinzen. We have here mapped out, and you have this on your canvas. It's just right. Okay, so if we are selecting now B1 to C11, and we're clicking on Insert, and we're scattering this out, what do we see? So we see now on the x-axis, we see a number of stressful life events, right, as our independent variable. So existential horizontal is number of stressful life events. So we have on the y-axis, we have, is it big enough? Can you see? So on the y-axis, you have now the DDI score, this back depression inventory score. So what can we say by just looking at it? So we see that there's quite some variation. We see trend-wise that it's rather increasing, right? So the more life events, 1, 2, 3, 4, 5, the more of an increase you will see in your depression score, which also makes sense when you think about it conceptually, right? It's like the more stressful life events, the more depressed you are, kind of makes sense, right? So if you fit now a add chart element and you fit a line through that, you get now a line that is essentially your regression equation. So this is the equation that we will define by a slope and an intercept. Well, the intercept is for x equals 0. So this is our intercept. And the slope is essentially the increase from 0 to 1. So these two things we need to define this equation. So, okay, if we, and this is where Excel is kind of a nice tool to work with, because essentially Excel allows you to do that quite simply, but just clicking here on display equation on chart, you get y equals 3.24 plus 9.54. And when we look now at this chart, this intercept essentially is 9.5, and the increase, yeah, somewhere in the realm of like 3. So, but how are we calculating it? And this is now where things are getting a little tricky and important for the quiz and also for the final. So we are meant to first characterize the population. So we need to understand how does the population distribute. So firstly, we do an average of our number of stressful life events, which is 1.9. We create a standard deviation of our stressful life events, which here is 1.67. If we're doing this for our independent, for our dependent variable as well, we get an average of 15.7 with a variation of 9.4. Now next, we just need to calculate our m on our x minus m, which is our deviations, which is essentially stressful life events minus the average logged in. We have y minus my, this is mx, which is essentially our depression score minus our mean depression score, which gets us 8.3. We're basically continuing this order down. And now we just need to build, so we remember from the correlation coefficient that we derive the correlation coefficient by calculating the product between the deviations multiplying the deviations of x with the deviations of y, summing these products up and dividing it by the square root of the sum of squares. So firstly, then we need our product, which is essentially this multiplied by this. We continue this, and now we need the squares, which is x minus mx square and y minus my square, which is this squared and this squared. Good. This being said, we can carry on. We get our sum of squares, which is sum of this, and some of this. So these are our sums. So this is the sum of the product. This is the sum of squares. Now, simply, we are taking the product, the sum of the product. We're calculating our R by taking the 80.17 divided by the square root of this multiplied by this. Gives us an R of 0.57. So that's the correlation coefficient, which is considerably large. As per Cohen's definition, this is a large correlation or a strong correlation. So continuing now to think about what we need to do next. So we have thought and discussed the prediction of our y hat by multiplying our correlation coefficient with the set of x. Why the set of x? Because this is the determining and predicting independent variable. So if we are now mapping out a raw score of x, and we say we have no life events, 1 stressful life event, 2 stressful life events, 3, 4, and 5, we essentially firstly need to calculate the set score. Who remembers how to calculate the set score? You know?
You do the n minus mu over square root of n.
No, but it goes in that direction. Yeah, so we're calculating the individual score minus the mean, dividing it by the standard deviation. You remember we had the normal distribution that essentially has a peak, a mode, which is our center, which is our mean. And the set score allows us to characterize the distribution curve in terms of standard deviation. And you're doing that by basically building a difference of each individual score to the mean and to characterize that distance in number of standard deviations that this individual score is located away from the mean. So what you would be doing is set x equals this minus the mean, which we know is 1.9. And dividing it by the standard deviation, which is 1.67. So this gives us here a set of x. Locking that in allows us to drag the whole formula simply down. And we get now a list of set x. So what you see here is that, so we have a mean of 1.9, and the further the number is away from this mean, the more it increases in absolute value. So the 0 is 1.9 in terms of raw magnitude away from the mean of 1.9. In terms of sets, it's 1.14 standard deviations away from the mean. That's the interpretation of that set x. Please remember that for the final and just in general. Okay, so now we know the prediction of our set y hat is done by using the correlation coefficient multiplied by the set x. So our set y hat is this multiplied, not this, equals this multiplied by our set x. Gives us a set y hat. And what is that? That is easy. Oh. Of course, you need to lock it in. Page 18 needs to be locked in. So this gives us already an idea how set y hat will basically shape in the light of our set x. So now when you look at this equation, how you calculate set x, you're treating now the retransformation of your set y hat to an y hat in the very same fashion, right? So if you say, okay, this is a standardized score that basically indicates how far this raw score is located away from the mean in terms of standard deviation. So now replace that set x with a set y hat, use the mean of y and the standard deviation of y, you actually get your predicted y. And that's the beauty of a standardized regression equation, because you can use this to calculate now your raw scores by basically reversing this equation. So the way this is done is simple. You basically, you want to multiply the set x or the set y with your standard deviation of y. And then you just need this term to be added to that. That leaves you only the x or the y, essentially, in that estimation of the y hat, in our estimation of the y hat. So if you want to calculate the y hat, all you need to do is y hat equals your set y multiplied by your standard deviation of y plus your mean. That gives you an actual estimated y. So locking this in will allow to continue this equation and allow to complete this list. So what do you see? What is this? This essentially is using that data and utilizing this data that you have used to build this regression equation and build this scatter plot to build an equation that allows you to now quantify your predicted y. So your y hat essentially is now the predicted depression score when the number of stressful life events is 0. This 12.8 is the depression score when your number of stressful life events is 1, and so on and so on. So you essentially, you have already in there all the information you need to build your equation, right? So you have intercept is the y where the x equals 0. This is this, right? This is your intercept. And we know this to be true because when we look at this equation, Excel says the same. So you, thank you. Well, this is with this tool we could have fixed it. Okay, so essentially you know this to be true because Excel says 3.241 and 9.54. So looking at this data, thinking about it conceptually, we have now the intercept. We know when x equals 0, 9.5 is the y. How can we get now the slope? When the definition of the slope is that it is the increase of y with an increase of 1 of the independent variable x. Think about it. You have the x. You have your predicted y. Bingo. You're just subtracting your predicted y hat at the number of stressful life events of 1 from the back depression inventory score of when x equals 0. And the difference is your slope. So slope equals this y hat minus this y hat gets you 3.241. Kind of logical, right? And this is where this all comes together. And this being said, we can now use this to express our equation, which is now essentially, what is it? Standardized regression. Come on, oh yeah, oh yeah. So this equation is now essentially y hat equals 9.542 plus 3.241 multiplied by x. So this is the first regression equation that we have solved. So it's simple, right? It's not terribly complicated. So the problem is likely the transition from this to this, but you got to keep in mind when you standardize things, everything is under the assumption it's a normal distribution, and all these relationships with a known correlation coefficient that gives you kind of already the direction and kind of that angle of association. Then you basically utilize it to standardize it and to relate it to each other in a standardized fashion with the standardized regression equation, and then you just need to transform it to get to your raw score. That's all that is being done. Good. Any questions? Just make sure what is really an absolute take-home message is that relationship with the correlation coefficient, that the correlation coefficient allows to build the bridge between set x and set y, that this regression equation essentially allows you to predict your dependent variable using the intercept and the slope. You will 100% have on your quizzes and finals a question around this equation. This is, I guarantee that. So please make sure to really understand the concept. Okay. Any questions with anything? Yes.
Can you just repeat
the key message is that the correlation coefficient allows you to relate standardized x scores to standardized y scores, and then by transforming the standardized y hat, so this predicted y, back to essentially get an actual score, an actual predicted y score, so a dependent variable score. And by using this equation, and you get here an intercept and a slope. And this intercept is where x equals 0. That's your dependent variable when you have an x equals 0. And then you have the slope is the increase with an increase in the independent variable x, which for the number of stressful life events is considerably simple, right? So you basically have one life event that increases by 3.2, then you have another life event that again increases by 3.2. So it's basically additive. It's an additive model. And you actually use it to predict the actual score, which is not true for more advanced regression methods, but for this simplest form, it's true. Good. Okay. So we did the calculation. Now we essentially found our way to get to our regression equation. We have calculated actual slope and intercept. And essentially what we want to have is a line, which is essentially that equation, that regression equation allowing for the estimation. So this is when you would depict that line on 3 points. These are the predicted points. We predicted 0, we predicted 1. You can predict 1 more to fit it through, but this is basically along with what you have seen. And this is the same line of best fit that we have computed in Excel. So this is essentially a very easy way to fit a line, which is essentially the least square approach, minimizing the distance between each individual point at each entry of x and that predicted y hat. And this is what is being used to quantify your predicted value. So the problem obviously with predictors are that they're full of errors, and you have an error with each entry. Unfortunately, this usually follows a certain pattern that with higher values, you often have more inaccurate estimates, but you do analysis of this variability in a very focused manner, and there are methods how you actually quantify that. So the variability can be measured, and this is measured by the standard error of the estimate. And this is basically the distance between each individual point and the predicted value on the y-axis based on that line of best fit. So this distance is essentially called the so-called residual error. So it's a residual error that is built between the actual observation and your prediction. So when you are asked to compare the prediction between the left or the right graph, which one would you think is the better prediction? Just intuitively, when you look at that prediction. Exactly, the left. And why? Because the distance between each predicted point and the actual observation is small. And of course, this can be quantified, and this quantification is done with the so-called coefficient of determination, which is, you know the term already from the ANOVA. If you remember, we had with the ANOVA, we had the so-called R squared, which was our effect size. And this effect size, what it was with the ANOVA, it was basically the variability between the groups divided by, or the variance between the groups divided by the variance within the groups, because it's only groups. Now it's essentially individual points. So we're moving away from groups. We have continuous variables, but the concept remains the same, because the group had a certain error, and if you would fit a line through those group means, you would get a certain error and a certain difference. This is just using the same concept to employ it on the individual points. And you're doing that by essentially quantifying the sum of squares. So we always have a variability, we have an error. This is our deviations. We're squaring the deviations, and we see how much does that differ from each other. We're quantifying these deviations, we're squaring them, and we get sum of squares. And if we have sum of squares total minus the sum of squares of error, which is the error of our prediction, divided by the sum of squares total, that gets us essentially to our R squared, which is a number between 0 and 1, and is quantifying the proportion of variability in your scatter that is being predicted, successfully predicted by your equation, by your regression function. How are we doing that? Now we will do this in a second. We're doing it in essence by having a depression score, which is the real y. We're quantifying a mean, which is then essentially that error, which we've quantified already. And the squared error is our sum of squares. But the leftover variability after employing that regression equation is actually what we are after. So the way you would quantify this is by quantifying now. So hypothetically, you could also say, okay, so I have now a y hat. My y hat for individual one is calculated as intercept, which is 9.454, sorry, equals intercept, which is 9.542, plus your slope multiplied by the number of stressful life events. It's the equation, right? Intercept plus slope multiplied by number, plus number of stressful life events. So you have N18 plus O19 multiplied by number of stressful life events. Locking this in allows you now to calculate that residual deviation, the distance between the predicted from the actual observation. Bringing that all the way down allows you to quantify now the sum of squares of your regression. So that's the inaccuracy from your regression. Okay. So now this being said, we have now the sum of squares y hat. Oh no. We need to obviously sum this and square it. So that gets us to the inaccuracy of our equation. So if we carry on, we have a squared error here, which is now what we quantified already. So these are the differences. These are the inaccuracy of the y hat that we have quantified. Now the squared error of y minus y hat squared gives us these differences, which are essentially these differences, which are called residuals. This is the error and the inaccuracy of the prediction. So now, using this using this to essentially quantify now our r squared would now be the sum of squared total minus the sum of squares of this error. This is now y hat minus y squared would essentially now allow us to quantify exactly this r squared that is being calculated here also by Excel. And Excel also allows for you to quantify the very same, not in this case. Doesn't do it. Doesn't do it. Oh, yeah. So we have an r square of 0.33. So essentially, if we have now a sum of squared total divided by our sum of squares, we determine an error associated with using the mean as a predictor. We determine the error associated with the regression equation as the predictor. We subtract the error associated with the regression equation from the error associated with the mean. So we're doing now a calculation of, no, this doesn't make any sense. Minus y. Oh, not for them. So this is y hat plus slope multiplied by an actual number of stress for life events. Oh yeah, so that was okay. So now we have this multiplied by this. That's this multiplied by this. This gets us our y hat. Y hat. So y hat minus y squared gets us now to y minus, this is the actual observed back depression inventory. So this is the deviation, that's the actual residual. Squaring this gets you to your sum of square of the regression. So this is now essentially what you are interested in. So you have now sum of square total minus your sum of square error, which is the error of your prediction, divided by sum of square total. So your R squared is now this 788 minus your 526, the error of your prediction, divided by your total sum of squares. And this comes to your 0.33, which is consistent with that R squared that you have determined with your fit line. Of note, if you calculate your R squared using the R, in a simple linear regression, you're allowed to do that. You essentially can take your correlation coefficient and square it, gets you to the same result. So you're essentially looking at a considerably medium well model because you're only explaining 33% of your variability using your regression equation. Okay. Any questions on that so far? So again, regression equation allows you to predict values. You're doing that by relating the correlation coefficient to your set score of the independent variable and predicting the standardized set score for your dependent variable. Allows you to develop by using the predicted set score for y and calculating the actual raw score from that for two values that you're actually interested in, which is your intercept, where x equals 0, and for 1, where x equals 1, allows you to calculate the intercept and as well the increase from 0 to 1, allows you to quantify and define the regression equation. This regression equation you can then use to calculate for each of your 10 individuals that have responded to your survey, to your back depression inventory, the depression score. This depression score, you're basically comparing this predicted depression score, you're comparing to the actually given answer, to the actual score that a participant has scored on the inventory. And this essentially, this difference, this error deriving from this comparison will allow for you to quantify how well does your regression function work and how much of the variability in your data is explained by your regression equation. So in our case here, by using the overall variability, which is the sum of squares of y, divided by the difference between the total sum of squares and the sum of squares that is being explained here by your regression equation, allows you to essentially quantify the proportionate reduction of error by the regression function by quantifying the coefficient of determination. And I think this is where we'll stop here because that's where I stopped with the other class. And we will continue on that topic on Wednesday. If there are any questions, let me know. If not, we'll see you on Wednesday. Any questions from you on Zoom? Oh, you looked at it.